Hey everybody, welcome to our first notes. Let's get this started, okay? So today we're talking about change in tandem, which means that we're changing at the same time alternatively. We're talking about functions. You've studied functions before. We're going to add to some of that understanding. We're going to also review some of those ideas right now. So a function is a mathematical relation that maps a set of input values to a set of output values, okay? Such that each input value is mapped exactly to one output value. So the definition of a function is that every input has one output value. That's it. So all of our input values, we call that set the domain. And we call that, those are the set of our independent variables. Usually we call this X, but it can also be other variables. A really common one is T for time. Let's talk about output values. So the output values, that set of variables, or that set of values is called the range, and these are dependent. They're dependent on the independent variable. And typically we use Y for this, but it can be other things as well. Remember that when we're looking at different functions that could look like different things, that our independent variable is typically this x-axis or the independent axis. The independent axis is always along the horizontal axis, and that our output axis, or we should say dependent axis, is usually the y, or you can say that this is f of x, the function of x, okay? So here we go. Often it's useful to use other variables that help us recognize representation. For example, if we throw a football, since we're in football season, right? So if we're looking for a football, let's just say we can use this graph right here. The things that can tell us where a football is going to be is, number one is, I want to know how high that football will be thrown, but also that depends on the amount of time or the number of seconds since the football was thrown. So in this case, our independent variable is t for time in seconds, and the height of the football, we can say h of t, is dependent on that t or time variable. So we call this the height. So, when the guy holding the ball, let's say it's right here, he kicks it, and the ball looks something like this. It goes up and then it comes back down. We see that at 0, the height of the ball is 0. But as time goes on, we see that the height has a maximum height of a certain amount of time, and then it comes back down to the ground eventually. So this function, we would say h of t, or the height, is a function of time, where t is our input variable and h, or our height, is our output variable. Okay, so let's practice this a little bit. So if we say w of x is a function where w is the amount of water in the pool measured in gallons, and x is the length of the pool. So which one's the input, which one's the output? Remember that x is our input. Whoopsie. And w is the output variable. What does the independent variable represent? Remember, our input, our independent variable, is x. So x, which is the length of the pool. And then what's the dependent variable? Remember, the dependent variable in this case is w, which is the amount of water in the pool. Or we could say the amount of gallons in the pool. Okay? These two variables will vary in tandem. So they'll vary together according to the function rule that's established. This rule can be expressed these ways: verbally, analytically, numerically, and graphically. I also like to call verbally words, and analytically can be algebraically. Okay, and together they say G for graphically, N numerically, A is analytically or algebraically, and with words, verbally, we get to gnaw on these functions or describe them in these 4 ways. So throughout this course, you will be using all 4 of these expressions to represent a function. Get used to gnawing on your functions, okay? So first one, let's do this verbally or with words, okay? So if I were to describe an increasing function, it's as the input values increase, the output values always increase, okay? Analytically, if I'm looking at an increasing function, for all values of a and b on the interval, if a is less than b, then f of a should be less than f of b. And graphically, let's look at this. Okay, so if here's an increasing function, here's a value, we'll call it a, it could be anywhere on the x-axis, and a value b, which is greater than that value of a. I'm going to follow these up to the function. This point right here is f of a, or the function value when a is the input, and this point here is f of b, which is the value of the function when b is input. Okay, so we can see, use my little pointer here. If a is less than b, that's what we're saying here, then f of a is less than or lower than f of b. So it's higher than f of a as well. And then keep in mind this is our x axis and this is our f of x axis or the y axis. All right, turn the page. More than halfway done. So now let's describe a decreasing function. So I'm going to have you guys pause right here. I want you to try this on your own. See if you can describe it verbally, analytically, and graphically. All right, let's see how you did. So verbally, as the input values increase, for it to be decreasing, the output will always decrease. Hopefully you got that right. Analytically, for all a and b in the interval, if a is less than b, then if it's decreasing, then f of a will have to be greater than f of b. So graphically, let's draw a decreasing function. Looks something like this. Let's pick a value of a. So here's a value of b that's greater than a. And if I follow these up to the function, here's f of a, and here's f of b. So what we're saying is, hey, for this value of a is less than b, if I follow this up, if it's decreasing, that means this y value is higher than this b value. And that's the definition on if it is a decreasing function. So for example, we can also look at this numerically. So here's a T-chart of values on a function where f is the function. This can either be increasing or decreasing, but not both. So we're going to discover whether or not it's increasing or decreasing, and let's figure out how. So if I can't see it, how can we know? Well, let's look at what's happening to x. So 4 to 6 is increasing, this is increasing, this is increasing. So they're increasing every time. So in this case, a is less than b. Let's see what happens to the y or the f of x values. Here we're increasing, 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 and increasing. So because as a and b is increasing, so is f of x, we know this must be an increasing function. So we say f must be increasing on the interval. So where is x increasing from? It's increasing from 4 to 20. So x is between 4 and 20 because it must be increasing because for all values, a and b, the interval then the function value of a is always less than the function value of b. So let's talk about now and analyzing the functions graph. So let's talk about where zeros are. So here's the first one. A zero is where the graph intersects the x-axis or the independent axis when the output is 0. So where do we see that? Well, we see that here when the output is 0, meaning the y value is 0. So here's where those zeros are. So here's a 0, where the y value or the output value is 0, okay? Let's talk about where the y-intercept is. Y-intercepts are when the graph intersects the y-axis or the dependent axis, and when the input is 0. So when the x is 0. So where do we see this? We see this right here. So this is an y-intercept, and when the x value or the input is 0. Okay. Okay. Concavity. So let's talk about concave up. So I want you to think about things that are, this is something that you've never seen before either. This is a new idea to honors pre-calculus. Concave up is like a cup. It can hold water. So if I were to take a bucket and dump it on this function, what part of this function would hold water? Well, I know it would kind of bounce on the left side of the function, but we can see that it would start to hold water here, right? So this is where we're concave up because it acts like a cup. So we can say, hey, this area here is concave up, okay? Concave down looks like a frown, and it looks like it's going up. So here's our frown part of our function here. So this is our concave down, okay? If a function's a straight line, it does not have concavity because there's no curve. And let's talk about this other idea, which is called a point of inflection. And a point of inflection is where concavity changes. So concavity will go from concave up to concave down, or concave down to concave up. So if I'm looking at this, I can see here's concave down, concave down, concave down, concave down, concave down, and whoop, right here is about where it starts to switch to that concave up. So this point right here in green is our point of inflection because it's where it changes from concave up to concave down. So now let's analyze this next one. Okay, so on our independent axis, we see these values of G, H, I, J, K, L, M. Those are just specific value, unspecific values on the x-axis. They could correlate to real numbers, but they're letters instead. Okay, so let's look at this. Use the graph of F to answer the questions below. So when is the graph concave up? So hopefully, I want you to pause this. I want you to really look at where the concave up or where it acts like a cup. Go ahead, pause it. All right, I hope that you, while you were paused, you could see that this would hold water to about right there, and that this would hold water to about right here as well. So I'm actually going to, instead of that, let me highlight that. Okay, so this is where it's going to start to kind of hold water here and here. So this is where we have that concave up idea, okay? So when is the graph concave up? Let's describe those numbers. So we've got G to, and this point right here is I. And actually, it goes past G, doesn't it? It goes to negative infinity. This goes to positive infinity. So, and then it also starts to hold water from K, and it goes past M all the way to positive infinity. So let's describe that. So it holds water when X is less than I, and when X is in between or after K. So we say X is greater than K. We're going to use this new way, instead of just inequalities, we're going to use something called interval notation, where we use brackets or parentheses. So parentheses is on the left side, this is our starting value. And on the right side, this is our ending value. And we use brackets when it's kind of an open circle where it cannot touch that ending value. And we use brackets, this is our starting and this is our ending, when it can touch those ending values. So we'll use some more examples as we go, but for now, it doesn't actually, on I, we're going to have an open value there because on I, it's not actually still concave up, it ends there. So we say from negative infinity to I, we're concave up. And then if we have a second thing, we say union to list the second one. Sorry, I'm kind of overlapping here. And then we say from K to infinity. Now let's talk about where we are concave down. So concave down, remember, is like a frown. So that's right here to here. So we say, hey, it's concave down from when X is between I and K. And in interval notation, we say, hey, from I to K, we are concave down. Let's find those zeros again. Remember, zeros are when it crosses that independent axis. So one's here and one's here. Here's those zeros. So when X is the value of G and when X is the value of M, it's not a range, it's those specific values. Let's look for those y-intercepts. We know it happens on the y-axis or the dependent axis. And we know that it happens when y is that value, and it happens to be A. When is the graph increasing? So we're increasing when it goes upwards from left to right. So we can see that it starts to go upwards here. And we see that it also starts to go upwards here. So how do we say increasing? So we say increasing from this point here, when X is between H and this point, actually this point right here, J. Okay. We can also see it increasing here from L all the way to infinity. So we can say when X is greater than L. So let's write that in interval notation. So from H to J, and union from L to infinity. And then lastly, when is the graph decreasing? So we see decreasing when it's going downwards from left to right. So here's a decrease, here's a decrease, okay? So we see from negative infinity to H. So when X is between, let's actually X is greater than, or excuse me, less than H. And then we also see it from J to L. So when X is between J to L. So let's write that in interval notation. So we say from negative infinity to H, union J to L. All right, y'all, come ready in the next class, and then we'll start our practice together. Bye.